Welcome to this webinar. My name is Bülent Taşdelen. I am working as Business Development Manager at Kistler. Today I'm going to talk about how to set up stationary dynamometers and how to utilize our software Dynoware. We will talk about both the software and hardware setup. I will also give hints about signal analysis and important parameters. I hope that the webinar will be useful for you and in your projects you can utilize this webinar and our measurement chain for your work, and that you will, of course, at the end of the presentation have a better understanding on how to utilize our products. Let's start. So the webinar is divided into 4 main chapters. In the first chapter, I will talk about the installation of the hardware and software by taking one of our stationary dynamometers and a LabAmp as examples. And then in the second chapter, we will talk about how to make the setup of the software. Later on, I will show the analysis tools that are possible in our software's Dynoware. And at the end, we will finalize by talking about some important parameters and give some hints about troubleshooting. Let's start with the installation. So we will start with the installing of the required softwares. You can find them in our web page under the products, and then you go to the 5167, which is our LabAmp that we utilize. You will install Network Setup Wizard and also the Dynoware software, which I will explain later on. When it comes to the installation of the software Dynoware, what you have to do is that you need to unpack the downloaded zip file, click on the Kistler Setup exe file, select Continue with the installation, and select the install Dynoware software and follow the instructions. So, in that order. You will need to choose to install the complete package in order to have it as smooth as possible, the installation process. So please choose the complete, and then it will make the installations of the necessary softwares. When it comes to our hardwares, you can see that this picture is covering what is needed. You have your LabAmp here, our amplifier and data acquisition box. You have the Ethernet cable that takes the measurement from that DAQ and amplifier box to our computer with an Ethernet cable. We have our dynamometer, in this case 9139, as I said. We have a high insulation cable. We have USB license dongle, the power cable to the LabAmp, and we need the all seal ring and screws to connect the high insulation cable to the dynamometer. Please really ensure that the all seal ring is always put in the cable, which I will show later. When it comes to fastening the workpiece, as you know, our dynamometers are designed in different ways. But if you look to this version where the sensors are horizontally preloaded, you have your workpiece region here, marked with the red rectangular here. So you need to ensure that you fasten the workpieces on that region. We can start with unplugging the cover from the dynamometer. You will need the 2 screws and the all seal. And then we start with taking off the cover, save it in a plastic bag. We take the cable end that is suiting to the dynamometer, take off the cover on the cable, and we put the all seal. As I said, this is a very important part because this inhibits the cutting fluids and humidity and so on enter to the cable, which can destroy the cable and affect the measurement. So do not forget the all seal ring. As you can see that in this case, you see that we have 5 pins here, 1 in the middle and 3 on the bottom. So if you look to the dynamometer, there will be only one way to fit this into the dynamometer. As you can see, for instance, there's 3 pins here match the 3 pins there. So put it there and then screw the cable. If we look to the other side of the cable, of course, this will then enter and will be put into our LabAmp here. Yeah, you take off the covers in both of them, place carefully the cable in, and then screw the bushing to ensure that it is fastened. And put the covers back on each other. On the LabAmp, we have the power cable, and we need the Ethernet cable that brings the data from the data acquisition LabAmp to the computer. We have the USB dongle that you place in your USB in to your computer, and the red LED light here should be on when it's working. Very seldom that it doesn't work, then you need to try different USB ingångs here on your the ports, different ports. You need to test. If it doesn't work, then what you need to do is that you need to uninstall the dongle driver. It's called Sentinel Hasp Runtime. It's in the same package as you have the Dynoware package. If it really doesn't work again, then you need to uninstall the Dynoware and completely reinstall. If you look to our LabAmp here, when the Dynoware is completely installed, when it's time, what we do is that we power up the cable when the LabAmp is switched off, be connected to the electricity, start the software and the computer, and then start the LabAmp afterwards. When we start the LabAmp, you will see that the yellow lights, it will be blinking on all channels. And when the setup is ready, all channels will blink blue. Then you know that it's time to make your setup, and you can make the measurement. The LabAmp, as we said, is connected through an Ethernet cable, so it has its own IP address, which is changing every time you switch on and then you connect again. So what we need to do is that we need to open up the KISS and network setup wizard that we installed in the beginning, if you remember. So you go to your start menu here and then write setup wizard, and it will show up. You press network setup wizard here, and then it will try to find the LabAmp. You need to click to the identify button here. Sometimes you need to wait until around 2 minutes and press the refresh button. Sometimes you need to repeat this procedure, identify and refresh. And when it is found, you will see that it appears in the menu here with an IP address. Then it means that there's a connection between the computer and the LabAmp. So let's go to the software setup. In this slide, I will show you the main steps that we will follow while setting up and using our Dynoware. We will start with the hardware settings, where we will make the connection to our data acquisition system and make the channel settings. Then we will move into acquisition settings, where we will enter the sampling rates, the sampling time, the filters, file names, and directories that we will save our files into. Then we will move into the step 3, documentation, where we can enter titles and remarks and the cutting conditions. In step 4, the setup views, we will choose the type of the plots, which channels to view, and so on. And then at the end, we can start the acquisition. So we go to hardware button here, setup button. We need to choose the right hardware in the drop down menu here. We choose LabAmp. If there is an old version or devices left in the software, we need to remove it first and click again add to be really sure that it is finding the right IP address. And then you need to press the find device button and press identify device if it doesn't show up here. And later on, refresh the list also. And then when it finds, you will see that it shows up here, even also in this software of the Dynoware software. and then you need to press OK. And when correctly done, the IP addresses that you can see in the list here in your Dynoware software and what you have found and connected in your setup wizard, they should match, as you can see here. In this slide, I'm going to show you how to make the settings of the hardware that we are connected to. If you remember in the previous slide, we have put up the connection between our AD board, in this case our LabAmp system with 8 channels. You can already see here that we have 8 channels. We have also LabAmp systems for 4 channels. And when you are connected to the LabAmp system with 4 channels, you will have only 4 channels to work with here. So what we will do is that we will take the same labeling that we propose in our datasheets for that specific dynamometer, as you can see here, enter the same names to be more consistent and easy to use. Later on, we will add the sensitivities and measurement ranges that you can find in the calibration sheets. And then at the end, we will enter also the filters that are needed for the data acquisition. Depending on the measurement system, we advise you to choose the filter settings here between 3 to 5 of the natural frequencies of the system that you're utilizing. The time constant for cutting force measurement is long. Here you can also choose to start the acquisition via the software by choosing on start acquisition here. And you can also click in here where if you would like to see this dialog option between the acquisitions. So let's go to force and moment calculation. As I said, here in the multi-channel menu, we had the physical channels, as you can see also here, the physical channels. If we choose an off here, this means that we can only measure and see the physical channels. But if you would like to automatically calculate the orthogonal forces and even the moments here around those points and axes, then we need to choose the type here. So let us, in this case, we choose type 4 so that we can measure orthogonal forces from these physical channels, measurements that we can do with our dynamometer. Now we would like to measure the orthogonal forces and the moments. But if you choose one of those, you need to also enter the distances as shown here. That is specific for that dynamometer, and that can be also found in the datasheet of the dynamometer. So now let's move on to the acquisition settings. You press that button and then that menu shows up here. We start with the parameters. We write down here the measurement time that we would like to make the measurement, the sampling rate, and also if automatic measurement cycles or start and stop can be chosen here. Then if you would like to have a delay time, trigger delay time, you can put it here. Then it will have a delay after the triggering. If you want to save the files as a DWD file, you need to choose here. If you want to see the measurements also after each measurement, you click here, display data. And if you would like to export each measurement, you need to also click here, and then I will show how to configure. And again, if you would like to also see the real-time updates during the acquisition, you need to click here, that button. We write the name of the file here and choose append index to the file name, because then it will add 1, 2, 3, 4 and progressive numbers here in each file name so that you don't mix them up. And here you have the directory that is being saved. If you want to save this configuration, you click here. So as I said before, if you would like to configure also this export file, you press the configure button here. You can choose the channels that you would like to export here, the directory that you would like to save them, and also the value delimiter. If you would like to export, for instance, to Excel, or you would like to save as a CSV file and so on. If we now move on to the physical channels here, you need to choose the channels that you would like to make the acquisition. So we choose all of them, ensure really that you have it. If you would like to use any digital or analog triggering value, you need to click also here, the channels that you want to use as a triggering. And then of course, if you choose the triggering here, digital or analog, then you have to give the absolute or relative values here together with the units. But we choose on a key. So it means that when we press the button, it will make the measurement, and when it is done, after that, that measurement time as we have added here, then it will stop. Yeah. So, and then if you go on to the calculated channels, here you can see the calculated channels. And those were, if you remember, the orthogonal forces and the moments. If you would like to add additional channels because you would like to make additional calculations, you do it in the data manipulation, but you need the extra channels, which you do it in, which you can add it if you go to the options menu in the Dynoware and then add extra channel, then it will show up here. The data manipulation is where you add which kind of manipulations you want to do. For instance, you can choose the first channel plus the second channel, and the result can be something that you would like to also get automatically after each measurement. When it comes to documentation, you write, when it comes to the document titles and remarks, any remarks that you may have here. And if you choose the cutting force documentation mode here, then you can also add the cutting conditions that you have used, and it will be saved. If you want this menu to show up each time, then you choose show documentation between acquisition cycles, and then you press apply. When it comes to the setup views here, what we do here is that we choose the type of the plots that we would like to see. So you will have a multi-channels with the Y and T. So in the time domain, for instance, as a default, you press the details. Here you can choose the channels that you would like to make the plots of, the colors of those channels, and then also, of course, the type of the plots, either measurement in time domain or channel versus another channel, statistic, frequency domain, or even polar diagrams. And that is only valid, of course, for the moment measurements in the rotating dynamometers. Then how to start the measurement. You press this icon, the play button, of course, since we have chosen this menu to show up, it shows up here again. Yeah, so you can, again, if you have an additional information, you can put it here. It will show up the settings. And as I said before, if you don't want those to show up, you just take out the clicking here. You press OK, and then you press Go. Then you make the measurement. The software Dynoware enables you to save your configuration files so that you can go back and reload them. And also, as I mentioned, also load the configurations that you have saved previously. Let's have a look to some basic functions of the analysis now. So we make the measurement, we have the measurement here, and if you want to make some editing and saved in those edited versions or see only some specific channels, you press the new view button here, and then you can press the edit view, for instance, here. You can change, for instance, the color of the certain channels, or take out certain channels and choose in different plots and so on. So you make the editing here. If you press the cursor buttons here, you place the cursors by left clicking and then moving them, and then you will get the statistic here between the cursors. If you would like to make some sort of frequency function of that measurement, you click on this button here, and then you place your cursor again, and then you will see the measurement in the frequency domain for those channels that you have chosen. If you hold the right-click mouse, you can zoom for all plots. That is valid for all plots. If you double right-click, it will unzoom. If you want to change the scaling of FFT, you need to go to the options, FFT scaling, and then change the scale. In this case, we're talking about the FFT tool window here. then you can choose logarithmic or linear. You can also change the scaling of the main FFT graph, and the main FFT graph can be chosen in the wave setup. As you remember, is one of the options here. That was the FFT here. You can put vertical and horizontal grids, for instance, for your analysis purposes. You can get statistical also in the view here. If you press this statistics button here, and then it will give you some mean, maximum, and integral RMS values for those channels when you place between the cursors. When you place the cursors, the drift compensation of the selected channels, you need to press that button and then choose the channel that you would like to make the drift. You can choose only one channel or two channels, whatever. And then when you place the cursor, the software itself, it will take out the possible temperature drift that you may have between the cursors. Manual scaling, if you would like to change the scaling, you press that button and then you write the scale that you would like to have. If you would like to use additional filtering, you need to go to the analysis and filtering on in this case. And then what you need to do is that you need to choose the channels to make the filters, the type of the filters, the frequencies, and the order. So you choose the filter settings in the menu. Okay, let's demonstrate how filtering works in Dynoware. We can start with the row signal, as you can see here. There are no filters in this 3/4 components. Then what we do is that we use a low pass filter in 5 Hz at 5 Hz. So it means that frequencies which are larger than 5 Hz, they are cut off. Yeah, so that is what happens. And now let's compare with the high pass filter at 5 Hz instead. It means that frequencies which are smaller than 5 Hz, they are also cut off in this case. In this chapter now we are going to talk about some important parameters and some hints in order to make troubleshooting. As we said before, milling is a highly dynamic operation. You really need to understand and investigate first the dynamics of your system to understand what does a force measurement tell you and how to set up a correct data acquisition and signal analysis. You can perform a frequency analysis to understand the nature frequencies of your machine and process. You can place an accelerometer on your different machine parts and make measurements when the machine switches off in order to understand the frequencies of the mechanic itself and also any disturbances coming from outside machine. You can perform measurements when moving the slides, when rotating spindles, when coolant pumps on and off, and so on and so on. And at the end, of course, you can make the measurement while cutting. And then you will have a good understanding of which frequencies are coming from what. And you can take this one step further. You can perform model analysis to understand the deflection modes of your machine part with frequencies and amplitudes, with the help of, for instance, accelerometers and hammer in this case. So when you follow this and then really understand and investigate your system, then you will really understand when you make the force measurement what is what. And of course, it's also an important procedure for setting filters and sampling rate when you have this understanding. So the first step, as we said, determine the usable frequency range, and that can be done by the system identification. So you have to get a good picture of the frequency response of your system. And of course, this can be done, for instance, with accelerometers and hammer with force sensors also. So you know exactly what kind of nature frequencies your system has. And when you have that, then you can place your low pass filter, for instance, in your amplifier or in your post-processing in order to have this usable frequency range. And the low pass filter can be placed around third and fifth part of the natural frequency, as you can see here. And this will also determine your usable measurement range. And when you know the measurement range and your low-pass filter, then you can define your sampling frequency, and that should be at least 5 to 10 times the cutoff frequency of the low-pass filter. And of course, then you can perform your signal analysis in your post-processing. Let's start talking about low-pass filter. What is low-pass filter? Low-pass filter is the filter that enables you to measure and analyze the low frequencies and cut away the high frequencies. So using low-pass filters can be done in the charge amplifier, analog filtering. It can also be done digitally in your post-processing. And the advantage of doing it in the digitally in your post-processing is that then you don't lose the information that you have in analog signal, so that you can analyze and make filtering later on. So let's have a look to the cutting force measurement here. X-axis is the force measure at the time, and the y-axis is the forces. As you can see, we have 3 force components with some noise due to the many reasons, and when you apply low-pass filtering, you can get rid of the high frequencies. High-pass filter is the opposite of low-pass filter. High-pass filter enables you to measure and analyze high frequencies and cut away the low frequencies. Low frequencies can be, for instance, drift over longer measurement time, as you can see here. You can either choose a shorter time constant, it's basically a high-pass filter, or you can do the high-pass filtering, for instance, digitally in post-processing. And the only disadvantage is that the analog amplifier circuit may get overloaded. But what happens when we make the high-pass filter then on a signal having a drift? And you use the right frequency while filtering, then you can get rid of the drift in this case. This is a force measurement, as you can see, and we can perform partial FFT on that, and that is possible in our Dynoware. Why is that important? Because as you can see that the force measurement consists of different types of frequencies, and when you make the FFT analysis, you can see which kind of frequencies you have up to which amplitudes in your force measurement. And if you have done the investigation of the frequency response function of your machine and setup, then you know exactly what kind of frequencies are coming from the machine electrical system, the machine mechanical system, any possible equipment that can be affecting your measurement, and what kind of frequencies are coming purely from your chip formation. Choosing the right RPM is very important. We do not want to end up in resonance, so that's why we have to really understand the frequency response of our system. As you can see that this is a force measurement done by just exciting the system in the time domain, and you can convert it to the frequency domain, for instance, by utilizing our software. And then later on you can utilize the equation, as you can see here, the tooth passing frequency with the function of the RPM, and that RPM should end up in a frequency that is not close to or inside of these regions where you have the natural frequencies, because if you are too close or if you are inside, then you will have resonance vibrations. That's why you really have to follow the step by step and understand the frequency function of your system. Let's have a look of the type of the mountings here. So the dynamometer is mounted on the granite table by clamping close in one setup. In the other setup, as you can see, the dynamometer is installed with the screws, and in the third setup with the VC1000. And if you look to the now, when the force is excited in the zeta direction, the frequency response of our system, depending on this different type of clamping, will be different, as you can see in this plot here. And then you have the phase shift, can be seen here. So it's really important to understand the response of your system, and it is depending on the mounting, of course. What about the additional mass? As we know, the additional mass will also influence the natural frequencies. So in this setup, you can see the stationary dynamometer 9255 here, and then we have an additional mass and another dynamometer which is 9256, and then you have your workpiece and milling tool. So we have an additional mass of 35 kilogram in this case, where the 9255 will be being affected in this case. If you look to the force signal in X, Y, and zeta direction, you can see the red force signal coming from the 9255, so that is coming from the stationary dynamometer on the bottom, and the force signal 9256, the blue one, is coming from this dynamometer, so that is more close to the real chip formation, so to say. You can see that the approximate signal characteristics is quite similar, but you have some overshoots, as you can see here with the 9255. So when you have an additional mass, you have an overshoot when you make the measurement. You also have some sort of oscillations in the red signal. So the conclusion is that the smaller the additional mass, the better the signals represent the actual process. That is important. Let's also talk about the minimum force to be measured. And of course, this depends on the type of the dynamometer, type of the data acquisition, type of the amplifier being used in the measurement chain. So in many data sheets, as you can see, that it is given in the minimum Newton, and the explanation is that the force, the minimum force Fa, in this case, that can be measured in a system having a noise, the total noise Fs, is actually the 3 times larger than the total noise in that measurement chain. And the total noise is the noise summation of sensor and amplifier. Let's talk about the drift now. It is often recognized, as you can see here, as a slope in the measurement, either negative or positive, and it can be due to the electronics, it can be the insulation, or it can be because of the thermal effects. As we said in the former slide, we have the drift because of the electronics itself, which are given in the data sheets. So we can first check if the drift is normal or not. So what we do is that we connect the measurement chain, let the power on at least 30 minutes so that we come to the stable temperature in the electronics and in the measurement chain. We make one force measurement during at least 1 minute without any movement of neither machine tool or cables, no workpieces on, and so on. And then we calculated the force difference on the plot during 60 seconds. And that is actually the slope of the curve if you look to the force versus time plot, as you can see here. So what you do is that you take 2 forces, and then you take 2 times, and then you calculate the slope in Newton per second. And later on we continue by looking to the sensitivity of that specific dynamometer in the data sheets, so that we can convert the drift that we calculate in the plot from Newton per second to picocoulomb per second. Below is an example for 9129. As you can see, it is given in picocoulomb per Newton, in this case the sensitivity. So what we do is actually that we multiply the drift that we calculated from the plot times the sensitivity in order to find out it in terms of picocoulomb per second. And the reason we do is in the last step, and that is the electronics. In this case, for instance, the amplifier, it has a drift which is given in the data sheet, as you can see here. So by calculating the drift from the real measurement and then converting to the picocoulomb per second and double checking with the drift that is given in the data sheets, we are checking if that drift is normal or not. Then if we go now, let us assume that we have high levels of drift, and now it's time to understand where is the drift, yeah? So we have to find the origin of the drift. So examples of a stationary dynamometer is a measurement chain. You have dynamometer, as you can see here, you have dynamometers, the cables, and the electronics, yeah? So the drift can be originated from dynamometer, cable, or the electronics. So we have 3 positions where the drift may occur, and we need to find out where. So what we do is basically a similar way that I described before. Warm up your measurement equipment chain at least 30 minutes, yeah, at least 30 minutes to 1 hour to 1 hour, so that you can come to a very stable temperature in your measurement chain. And then you make 1 minute of measurement without any load with the whole measurement chain. So A, B, C. So dynamometer, cable, and electronics all connected. And then you can repeat the same measurement by disconnecting the dynamometer from the measurement chain, so only cable and electronics. And then you can also go further, 1 step further, and then this is disconnect also the cable, and also in this case only measure the drift in the electronics. So then if you compare 2, 3, and 4, most probably you will see a big difference in one of those steps, and then you will understand where the drift is coming from. Yeah. When it comes to the insulation drift, as we said before, when the total resistance is smaller than a value, the sinus starts to drifting. Often the connectors are polluted. That's why the resistance is reduced. So cleaning of the connectors should be the first troubleshooting action. If it doesn't help, the device must be repaired. Never use breath or compressed air from a pneumatic system to clean the connectors, as such systems may contain oil, dust, or humidity. Always use the Kistler 1003 cleaning spray. So thermal drift, of course, heat is involved during cutting process, and then the heat is traveling through the tool and the dynamometer, and it is causing some expansion in the metal, and that's one of the main reasons. You can utilize coolants to get rid of that and decrease it. Or what we have done here is that we have optimized our dynamometer design. Here is a picture. You can see that we have the cutting force measurement, comparison between 2 dynamometers. The dark blue is 9121, the old model, and 9129 is the new model, as you can see with the light blue. As you can see, there is a drift in the old model. And the standard design, or the old design, was that the ring sensors were located, as you can see, and preloaded vertically, while in the new model the sensors are preloaded horizontally, as you can see, to decrease the effect of the thermal expansion and thus the drift. As said before, the heat impact on the dynamometer is one of the main causes also of the thermal drift while making machining tests. One can make some simple solutions in order to improve this and solve such issues. One example, as you can see here, that you can have cover plates that is protecting the dynamometer from chips and from extensive coolant impact and so on. Another solution can be, in this case, it's presented by the researcher here, referred with the article. As you can see that our dynamometer is here, the grinding wheel is here, and that researcher has placed a ceramic plate on the dynamometer and then the workpiece on top of that, so that the impact of the heat going through the dynamometer is decreased. So let's make some final recommendations and summarize this webinar. Always store the measurement instruments in the room in which the measurements are to be taken, so that the temperature is pretty much the same. Where possible, leave the cable permanently connected to the sensor. Disabling and connecting and disconnecting always introduces a risk of oils and humidity and so on, and coolants entering to the connectors. Install the sensor exactly as instructed. Read the manual and get support from your Kistler representative for that if needed. Warm up the charge amplifier for at least, as we said, half an hour, 1 hour, so that it comes to a stable temperature. Set the sensitivity values on the charge amplifier exactly as stated in the calibration sheets. With force measurements, always work with the long time constant in your setup. Choose the measurement range so that the maximum measurement signal falls between 5 to 10 volt. For normal force measurements, filter the input signal to around 1/3 of the resonance frequency of the measurement setup as said before. Only switch the charge amplifier to operate immediately before you measure, or you can also start, of course, your measurement with the software. The reason is to start this just before you are cutting is that if you start the measurement while the machine is moving and making some accelerations, coolant pumps, rotations, and so on, then you will have some sort of disturbances in your measurement. Avoid changes in temperature during measurement. Calibrate the dynamometer every second year and after any possible overloading or crashes and so on. Make a control measurement with a known force occasionally. For instance, a 10 kilogram weight that gives around 98 Newton by placing known weight on the dynamometer, for instance. And make drift control as we show here occasionally. I hope that this has at least helped you to get some sort of step-by-step installation. And if you have, of course, additional questions, do not hesitate to contact your local KISTAR office.